Hi guys, welcome back. In this session, I would like to discuss another important program. So, the name of this problem is GCD. So, what is a GCD? The GCD is nothing but the greatest common divisor. So, how can we define mathematically what a GCD is? So, GCD is nothing but uh, okay. Let us say the GCD of A and B, the GCD of two values A and B can be found by checking all the factors of A, all the factors of B, and observing which of them is the greatest. So let us take two values like 8 and 12. So what are the factors of 8 and 12? Let us see. For 8 we have 1 is a factor, 2 is a factor, 4 is a factor, and 8 itself is a factor. And for 12, 1 is a factor, 2 is a factor, 3 is a factor, 4 is a factor, 6 is a factor, and 12 itself is a factor. So, what are the common factors that we have in this case? So we have 1 is a common factor, and 2 is a common factor, and 4 is a common factor. So out of these three common factors, 1, 2, and 4, which of them is the greatest? Okay, and we can also call these we can also call them as divisors also, because they can exactly divide this number. So when we divide 1 with 8, we'll get the remainder 0. So all these numbers are both factors as well as divisors. So out of these divisors, so which is the greatest divisor? So 4. So 4 can be said as the GCD of 8 and 12. Okay, now let us take another example. So we have observed a case where we can have GCD, but what if a GCD is not possible? So let us think for GCD, or let us say 17 and probably 19. So both of these are just prime numbers. So what could be their divisors? It's 1 and 17. For 19, it's 1 and 19. So what's common? So 1 is their greatest common divisor. So a prime numbers has this a special property where for any two prime numbers the greatest common divisor will always be 1. And also for any two numbers, if the greatest common divisor is 1, we can call them as co-primes. Yeah, and this function and along with the prime numbers theory is very critical for cryptography and network security, because a lot of functions are dependent on this single function. Okay, then how can we calculate GCD in an efficient way? So what is the algorithm for GCD? So it's a relatively simple algorithm. So we're gonna have two variables, right? A as well as B, and we're also going to keep track of another variable called reminder. And also remember, this reminder in program is nothing but A mod B. So this is a modulo operator. So using the modulo operator we can get the reminder. So we have this now. So now let us take the example of 8 and 2. Right, I'm going to use the same example. Right. So A is 8 and B is 12. Okay, so I have to divide uh, a larger number with the smaller number. So I'm going to divide 12 by 8. What am I gonna do? I'm gonna get 1 8 and my remainder is 4. Right, so my remainder is 4 in this case. Actually, we don't care about what this value is. We're only concerned with what the remainder is. So we have the remainder as 8. Now what are we gonna do? We are going to shift all these values to the left. So this value 12 is gonna come here, but actually I think 12 should be present here anyway. So 12 is going to be I mean 8 should be here. So I think we did a little mistake that A should always contain a lower value and B should have a higher value. So let us say we have 12 here and we have 8 here. Then there will be a shift like this. So 8 will come here, 8 will come here, 4 will come here. And now we need to again recalculate a reminder. So what will be the reminder? So the reminder will be, okay, I have to divide 8 with 4, and with the factor of 2 I can exactly get a reminder 0. So my reminder is 0. Now I'm again going to shift. Here is my 4 and here is my 0. And what is the uh, base condition for this algorithm? It's actually when p equals to 0, we are going to stop and return a, and a is going to be our answer. A is going to be our GCD. A will be considered as a GCD only when b becomes 0. So I hope this makes sense to you. Now let us take let us take an example where the GCD will be 1. So that's going to clear a lot of things. So now let us take two examples. Let me take let's say A is some 5 and B is 12. So what will be my reminder when I do 12 5? So it's 2, we'll get 10, and the reminder is 2. So my reminder is 2. Now do the shift. So again we did the same mistake here. So A has to be the largest value and B has to be the smallest value. So we'll have 12 here, we'll have 5 here. Okay, now 5 comes here, the reminder 2 comes here. Now what's the reminder? Now we have 5, use 2, so now the reminder is 1. Okay, now again shift them, so we'll get 2 here, we'll get 1 here. So what will be the reminder when I do this? So 2 upon 1 is always, we'll get 2 and we'll get a reminder 0. So you have 0 now. Okay, now shift them as well, and you get 1 here and you will get 0 here. And should we stop now since we have B value as 0? Yes, we should stop. And what is the GCD? Yes, it's 1. So this is the algorithm, guys, very intuitive one. So you have, I think we can derive the algorithm as well. So what have we done here? So firstly we'll be checking if A is greater than B. We should only do this operation when A is greater than B. Okay, if A is greater than B, then what am I doing? Okay, I'm actually calling this, okay, let us say this is some kind of function is happening here. Then what am I doing? I'm actually passing my B to the same function along with the reminder, right? Am I doing the same? So let us call this function as GCD. If this function is GCD, then I'm recursively calling that same function GCD, but now the arguments are different. Now what is the argument? B is one argument. What is the other argument? The other argument is the R. How can we get a reminder? It will be A mod B. Right. And what is the other case? So what if B is greater than A? In that case, what am I gonna do? I'm gonna say else. We're going to call GCD, but now since A is the smaller one, we're going to send A, and since B is the larger one, we're going to say B mod A. Done. So we are actually done with our general cases. Then what is our base case? So when should we stop? So we should do all of this when B is not equal to 0. If we have B is equal to 0, then we have to return A. So this is how a GCD works. So now let us code this and see if this works. Okay. Let's define a function called GCD. It will take two inputs, A and B. So initially we are checking if A is greater than B, then call GCD on B and A mod B. Right. If it's not the case, then call GCD on A and B mod A. Okay, this is gonna work, but until when should we do that? We should, I think the first condition that we have to check is if B is equal to 0, then we just have to return the A, right? So this is the GCD for me. Okay, now let's take inputs. Okay, let's take A, B into and B will be now let's print as well as call the GCD function on A and B. So I hope this works. Also, I forgot to mention that this algorithm was given by Euclid. So we also call this as the Euclidean algorithm. Now let's run this and see. Okay, enter A. So what's the example that we took recently? So A is 12 and B is 5. So A is 12 and B is 5. Then it's returning none. Why? Okay, what could be the issue? Let's check this. Probably I think we're comparing this instead of comparing, and maybe we can just ignore this case, right? Because it's not needed. So I'm gonna rewrite this a bit differently. So if B is equal to 0, I'm gonna return A. But if it is not, then I'm going to return the GCD of B comma A mod with B. This should still work because I have made much changes because I'll be careful that A has to be greater always. So we have to be careful while giving input. So let's say 12, B is 5, and yes, we get 1. Now let's run this for another input. Let's take 8 and it says 6. It should be 2. Yes, interesting. So this is how we implement the GCD. Using recursion is the best way of solving this kind of questions. And yeah, so this is all for today. We'll meet with another program.